we have Roger Blandford as our first speaker this semester. Roger Blandford received his PhD in Cambridge, UK in 1973, after which he took a faculty position at Caltech, which he held till 2003. After that, he moved to Stanford and KPAC, where he has been since then, and for which he's been the director at KPAC. Over his career, Roger has made major contributions on theoretical work on accretion and acceleration processes in various contexts of astrophysics, including supermassive black holes, or round supermassive black holes, active galactic nuclei, as well as supernova remnants and pulsar nebula, pulsar ring nebula. He has received a number of prizes, which I will not go into detail of them, and many of them, but they include the Heinemann Award by the AAS, the American Astronomical Society, the Warner Prize, as well as the Eddington Medal. And today, Roger will tell us about accelerating the universe.
Thank you very much, Marianne. Thank you very much for the kind invitation. I'm always glad to come back to NYU and New York, and I've had a very good day catching up with colleagues and friends from long ago, so thank you very much. I should perhaps explain that my title is tongue-in-cheek. For those of you expecting yet another talk about dark energy, you will be sorely disappointed. That's the last reference I will make to this, and I shall deal with the more prosaic business of the propensity of the universe to accelerate particles to high energy. So feel free to leave now if you okay. Let's perhaps just start. I was asked to make this a very general talk, and I'll put in some sort of details for the specialists more towards the end, but for at least the first half of this talk, I'm going to try and make it sort of a mile wide and an inch deep, so that you'll get some idea of the scope of the field nowadays without necessarily going into a lot of detail. But I will pick out one or two points towards the end of this talk. Okay, so this is a slide I like to show, and it shows what astronomers are privileged to deal with. I think of it as 140 octaves, about 20 grand pianos worth. There's about, in the electromagnetic spectrum, there's about half of that, from the recurring frequencies up to the gamma rays. And, but there's also, of course, cosmic rays, and directly, and we hope one day, indirectly, and we hope one day directly, gravitational radiation. There's neutrinos, of course. There's also a lot of physics beyond the standard model and all of that. There's the hope to detect dark matter, and in a sense we're doing astronomy at that, even if we don't have detections of dark matter particles. We're certainly doing astronomy by seeking them. And so there's a lot going on here, and in terms of energy, it's atto-electron volts to zeta-electron volts. For those of you who still use CGS units, that's 10 to the minus 18, and that's 10 to the plus 21. And I went to a talk recently that got these slightly confused, which is one of the larger mistakes you could make in this business. And of course, what goes on, just to make this clear, that's the Planck scale. So this is, you're seeing activity in the cosmos up to, directly up to about a millionth of the Planck scale in terms of energy, and indirectly probably much more. Okay, so just say a little bit by way of introduction about cosmic rays, and I'll come back to this. They were discovered, of course, famously now 101 years ago. Here by Victor Hess. Who a very brave man who went up in his balloon, and he was absolutely confident that he would return to Earth. It was unclear at what speed. And he was able to determine that the cosmic rays had an extraterrestrial origin, and this was sort of further amplified in a very interesting debate by Millikan and Compton. Compton was basically right. And then as we go to the higher energies, John Lindsay and so on, we see these particles all the way from actually below a GeV in the solar system, but the ones outside the solar system are basically, we know about a GeV, the rest mass of a proton, through now 12 orders of magnitude almost, at least inferentially up to the zeta electron volts. So just to give this, and this is the spectrum of what one sees, and I'll come back to this in a bit more detail further on, but this is only to give you, at least I hope, some scope of what the field is about. This is, you know, a large range of energy, and of course this TeV is the Zevatron, and the SSC we're sort of right down here, and if you say, well, the centre of mass energy is what counts, you're sort of up there in terms of, you know, hitting a stationary particle, but of course in the universe these particles hit fast-moving particles as well. And that's one of the reasons why I personally, and I know most of you were probably very terrified about Brookhaven and CERN bringing life as we know it to an end. But nature has already performed this experiment for us, and bad things have happened, but not necessarily attributable to these collisions of high-energy particles. Let me just say a little bit about the tools that we have to examine them, and I'm going to go through this very fast. I'm not wanting to, you know, go through an instrumental overview here, but just give you some idea of the scope that amplifies what I had on the first view graph. So here are some direct cosmic ray experiments. This is a low energy cosmic ray satellite. It's told us an awful lot about the composition of the very low energy particles, and exquisitely detailed research about the isotope and composition, which we've learned a lot. Here's a balloon experiment, the space station and so on, of which there's AMS, and this is actually Pamela. It's another satellite that's told us about the spectrum of the electrons and positrons at high energy. Here's one that's in the news. This is Voyager. I remember it being launched in 1977. Well, actually two of them, both of them being launched, and today NASA took it upon itself to announce to the world that Voyager 1, one of these two spacecraft, has passed not just through the termination shock of the solar wind, but through the heliopause, so it is now encountered the higher density interstellar medium, passing through a contact discontinuity, so it's now sampling interstellar gas and the associated plasma disturbances and so on. And this is a remarkable thing. You know, I had no conception when this was launched that it would still be delivering data at 100 AU, but it is. In fact, both of them are still functioning, and we've learned an awful lot about the behaviour of particles at shock fronts by its passage through the termination shock. I've had rather little to say about that. I just want you to know that we have a lot of in situ experiments, not just Voyager, but any other many other experiments in the heliosphere that are telling us directly how dilute cosmic plasmas behave. So here's one that's dear to my heart, which is Fermi Gamma Ray Space Telescope. This is an orbiting satellite. It just passed its 5th birthday, so it's made pictures of the whole sky. It has found all manner of cosmic sources. Basically, it sees the whole sky every 2 orbits, every 3 hours, and builds up the signal and so on. It's about 100 times more sensitive than its predecessor. It was a gamma ray telescope. That was what it was sold as, but it's also turned out that the noise for the gamma ray astronomers, the gamma rays come in about 3 a second, but the noise for the gamma ray astronomers are all the electrons and also positrons, and they have turned out to be a signal as well, because it made exquisite measurements of the spectrum, and also is now actually was able, somewhat controversially, to separate out the positrons using the geomagnetic field. Moving on, here's Fermi looks at gamma rays in the GeV range. Here's how we look at them in the TeV range. That's 1,000 times more energetic. And this is Hess. This is Hess, actually, this is Hess here in Namibia. That's me taking a picture of me taking a picture of me and so on. What it does is it looks for the Cherenkov flashes as these high-energy gamma rays come through the atmosphere. And you can see up to about 30 TeV or thereabouts. It now has about 150 sources. There are upgrades being planned as we speak. And I've got emails about that this morning. And here's the American version of Veritas in Arizona. This again has been a spectacular. You're doing astronomy by seeing sources, extra sources, galactic sources at about up to about 30 tera electron volts. So, you know, so these are the gamma rays that you see. So we obviously know a lot about the astronomy of those. Moving on, here are again telescopes that I'm using about these ones. These are been in orbit for a very long time, 50 years or more. Chandra and XMM Newton. These are the sort of workhorse X-ray telescopes that have done a huge amount. You'll see some of what they've done. And this is the new kid on the block, which I'm very happy to be associated with. It's a focusing hard X-ray telescope called NuSTAR, a much cheaper endeavor than the XMM and Chandra, but very, very successful and already making great discoveries. And you'll see just a glimpse of this in what I have to tell you. Okay, radio astronomy has not been holding back either. Of course, we've learned a lot about non-thermal and high-energy astrophysics from radio telescopes, but one thing that's happened is the very large array in New Mexico at Socorro, near Socorro, has been completely rebuilt with well over 10 times the sensitivity with new receivers, larger frequency range, better and so on. So it's effectively a completely new radio telescope. And then in Chile, ALMA is the big major millimeter and submillimeter telescope array, another interferometer in Chile at high altitude. And that again is brilliantly successful. The results that it has produced from basically 16 out of the 63 or so telescopes that it's going to have eventually, before too long, are already rewriting the science case on which it was sold. So I mean, you know, it's more straight out of the box. It's worked and it's delivered already wonderful science, and it's still only very much in its construction phase. So we're very excited about the prospect of these two facilities. Moving on, Auger. This is the premier facility for looking at the very highest energy, the so-called ultra-high energy cosmic rays. This is in Argentina. In a beautiful place up there, and it has two techniques. It uses water Cherenkov detectors for particles on the ground, and then it does a different type of atmospheric detection. It's actually nitrogen fluorescence that it sees, and this has been able to see an effect that was predicted, the so-called GZK effect. And this is the attenuation of cosmic rays by their interaction with the cosmic microwave background. This photopion production will happen. This is uncontroversial particle physics, or nuclear physics to be honest. And it does happen. We're seeing the effects of that, the details. I'll come back a little bit to this a little bit later. Sort of on the other side of the coin of this is to do not ultra high energy, but merely very high energy neutrino astronomy using a variety of at a variety of sites, but most famously now IceCube at the South Pole, and that again is starting to produce results. I'll say relatively little about that, but one's starting to see some of the very high energy neutrinos that are accelerated by cosmic, we think are accelerated by cosmic sources. So I'll have relatively little to say about that, but we'll come to that later. So moving on again. Okay, so I have forgotten to put this on the slide. There's basically 26 neutrinos that have been found in the last sort of data release that up to energies of about a peta-electron volts. So you can see we're getting information from the universe at the peta-electron volt scale, 1000 TeV and so on. Okay, moving on. So let's go back to our cosmic ray spectrum and ask where they come from, and let me give you some sort of working hypotheses, just to give you some grounding here. The lowest energy particles basically come from the solar system, from the sun, from solar flares, from Jupiter, from shock waves traveling through the interplanetary medium and the solar wind and so on. Most of these sort of particles with energies up to about 100 TeV, or maybe a few hundred TeV. Not quite sure what happens. The transitions up to the so-called knee in the spectrum, as it's known in the trade. They come from supernova remnants. There are other sources as well, but the majority of them probably come from supernova remnants. These are the explosions of massive stars, mostly of massive stars, that send giant shock waves out into the interstellar medium, and that accelerates particles. And then if you go up to higher energies, it's a bit of a mystery where the particles in this energy range come from. There are various credible sources. Probably the most popular one are the pulsars, but we're not absolutely sure about that. And here's the Crab Nebula with its pulsar in the middle of it. And then, again, if we go to the very high, the ultra high energy particles, the ones up to its source, they're about a zeta electron volts at source. If we ask where they come from, there are at least 4 putative sources out there. I'm going to try and sell you on the notion that in fact they come from giant clusters of galaxies. Here's the Perseus cluster of galaxies. It's an X-ray image of it. It looks like a Halloween mask, but in fact it's not a death's head. But there's an active galaxy in the middle of this cluster of galaxies. It has created giant double radio sources which have made these bubbles here like that. That's not the source, I believe, of these cosmic rays. I believe it's a much larger shock front, but I'll come back to that point again if there is time. Okay, so there's the supernova. So these are the, if you like, the sun, the supernova remnant, the pulsar, and the cluster of galaxies. Working hypothesis, we can discuss it. Okay, oh, and there's the LHC, and I'll come back to that. I made this sort of point about the Fermi and others. Not only the noise for the gamma ray astronomers is the signal for the particle physicists, because as you well know, the hunt is on to find dark matter, quite credibly supersymmetric particles below, on and above ground, below with the underground detectors, on ground with the LHC and so on, and above ground by looking for a cosmic annihilation with Fermi. And what we have so far is, I would say, exquisite upper limits from the putative cosmological sources that are somewhat constraining of the particle physics, options that you have. And then one of the things that there's been a lot of excitement about, and Neil Wiener just sent me an email. They can't be here for perfectly understandable reasons. He's been obviously actively involved in this, and here are 2 measurements that show the positron fraction rising as you go to higher energy. There is in fact a discrepancy between the AMS facility led by Sam Ting on Space Station and the Fermi measurements. I don't want to get into quite where resolving that discrepancy, but let's say, look at it on the right side and say both of them are clearly agreeing that the positron fraction is arising. It would be very nice if one could say that this is then evidence that we have found annihilation of dark matter. The sad truth is that the cosmic sources are at least as credible, if not more so, than the putative dark matter sources. But nonetheless, this is a very important connection, and just if you'd like me to editorialize a little bit here, one of the things that struck me in the 10 years that I spent working half-time at SLAC is the stunning indifference of most particle physics to cosmic ray physics. Not only, has cosmic ray physics been, the source of discovery for these 4 particles, of course, and it's in some sense the mother of particle physics. It is sort of like almost a matricide to have such disdain for it. But what matters in science, of course, is what you're doing now. And I think that with the dark matter connection, the ability to see interactions of particles with energies with far higher centre of mass energy than you'll ever make on the ground, there's real information there, real possibilities there. And if I can proselytize a little bit, I just think those in the particle physics community should be paying more attention to what modern cosmic ray investigations are doing. Okay, so commercial over. Okay, so here's supernova remnant. I'm just going to show you some recent highlights from observations just to get you some idea of you know, where we're going on. Again, I'm not going to make a great big description of this. Here's a famous supernova remnant discovered by Tycho Brahe, century, and basically what you see here is this spherical feature around the outside. That is the shock front pushed out by the expanding debris from the supernova explosion. And it's the X-ray emission, and this is prima facie evidence that there's a very efficient acceleration of relativistic electrons of high energy. These are the electron cosmic rays, not the protons, in the shock front created around. And this is a was an idea that it wasn't just in some sort of generic way the exploding supernova remnant that was responsible for accelerating the cosmic rays. It was actually physically, mechanistically, it was the shock front itself that did that acceleration. So the shock front was responsible, and here is the evidence of your eyes. You can see the shock front doing that. But we learned something else, somewhat to our surprise, is that shock fronts are not only agents for accelerating cosmic rays, they also as a side effect, are very efficient at magnifying magnetic fields. There's a little bit of field in the interstellar medium that gets stretched, and there's various ways of showing this. In the shock front, here's a bit of detail here, you can see some of the evidence of that. So you make sort of very strong magnetic fields, these shock fronts, not just very high energy particles. And in fact, they do go hand in hand. The particles are so energetic that you need to have to make strong magnetic fields together with them in order to make this work. Okay, let's move on. More recently, particularly using Fermi, it's been possible to demonstrate directly observationally what had to be true was that supernova remnants are not just responsible for making the cosmic ray electrons, they also accelerate the far more numerous and energetic, about 30 times more, cosmic ray protons. They don't radiate directly, but we do see the gamma rays that they produce in collisions with dense interstellar gas. So in the supernova remnants in dense environments, we're seeing the gamma rays that are produced from pion decay and that's right. And so here's the characteristic feature that was predicted from these supernova remnants, and it's prima facie evidence that cosmic rays are accelerated at the shock fronts associated with supernova remnants, and the bulk of the cosmic rays, up to a fraction of a peterelectron volt, come from this source. So it's prima facie evidence. This has come, only in the last 6 months, this evidence. So there's a field with a lot going on here. Okay, so let's go on a bit more. These are blazars, of course. Let me just explain what this is. I'll come back to this point a little bit, but for those who haven't been indoctrinated by the astrophysicists here, almost essentially every normal galaxy has a massive black hole in its nucleus. When fueled, or spun, this is a source of nuclear activity that can outshine the galaxy, and in particular it creates jets of outflows, and when they are pointed towards us, rather like this laser pointer here, when those jets are pointed towards us, we see them as very bright. Those are called blazars, and we see observations. We observe them throughout the electromagnetic spectrum, and so this is a black hole in the center of a galaxy. It's producing power more luminous, not than the star, but than the galaxy, billions of times more, and yet these sources of colossal radiation are able to vary. And there are variations, particularly at the TeV range, on timescales of minutes. That's extraordinary. That means naively that the sources are light minutes across, and it's outshining the whole galaxy. That is an extraordinary phenomenon, and cries out for an explanation. Clearly, the jets, it comes from the jets themselves. This short time is partly attributable, by no means completely attributable, by the material in the jet moving at high speed, with Lorentz factors of hundreds or so on. That's probably true. We have a lot of evidence about this. But there's also a lot of confusing observational evidence, and it looks like some of this emission is coming not from very close to the black hole, but from a much more extended region further out. This is a very confused observational situation at the moment, but there's every prospect that it will get sorted out, and we'll see where the emission is coming from. But wherever the source is, extended regions that are highly luminous find a way, this will be a theme that will follow up, of having very concentrated regions that may radiate power very efficiently with high variation. So that's going to be the challenge, the theory, if you like. And then here's a very good example of that. Here's the Crab Nebula. This is the most famous of the supernova rodents, I suppose. It's the Crab pulsar net. It spins 30 times a second. It makes a couple of jets, rather similar to those that you see in active galactic nuclei. It makes this X-ray emitting structure. The purple is the optical. And then a recent phenomenon that was discovered and has now been seen several times is that this region here that is light years across finds a way to isolate some small region to vary just in the gamma ray band, that's here, 400 MeV, that's in the gamma ray band, on timescales of hours. So it produces a huge power from a tiny region in this great big nebula here. It's light years across, and yet it varies on timescales of hours. That's a remarkable phenomenon. We do believe in special relativity, so that's why it's a remarkable phenomenon. Okay, let's move on. Okay, this is just making the point that this emission here is just in the gamma ray band. We've looked for it in the rest of the electromagnetic spectrum and seen nothing that goes along with it. Okay. Yeah. Okay, and then just to drive home this point of this is very much an active field with lots of discovery happening, on timescales of months. These are things that have happened just in the past few months. Firstly, New Star, which I mentioned, found a magnetar. A magnetar is a highly magnetized neutron star. Now, a normally magnetized neutron star is a mere 10 to the 12th Gauss surface field, 10 to the 8th Tesla for the modern amongst you. And a highly magnetized neutron star is about 300 times as stronger magnetic field, 10 to the 14 Gauss or thereabouts. And New Star has found one of these things in orbit around the black hole at our galactic center. That's a remarkable discovery, and we're learning a lot from looking at this. Here is one of these so-called blazars, Markarian 421. It went berserk about 3 months ago, and it's 100 times more powerful than it typically is, varying on timescales of hours, less than an hour. And again, we're able to look at it throughout the electromagnetic spectrum and learn what's going on. The sun has not been shy after being very dormant for a while. It has now been very active. And then one of the brightest gamma ray bursts, Andrew and others will tell you about those, and so on, has been seen. Got the most highest energy gamma rays. These outflow Lorentz factors have to be thousands. Highest energy gamma rays, and yet no neutrinos produced from it. That again has been a big discovery. So there's a lot sort of going on just in this general area. Okay, so, and then finally, and this is perhaps one of the most exciting developments, it's something that's been coming and going observationally, but now it seems to be really well established. There's a new class of fast radio transients, and these are a population of apparently high redshift objects. Nobody's identified one yet. But they appear to radiate 10 to the 39 ohms, which is not a huge amount of energy, but they radiate these in milliseconds. They're on the far side of the universe, they're like gamma ray bursts, and there's about one of these every 5 minutes going on in the universe. And so it's a very active sort of area trying to figure out what these are, but they're at least as important a discovery, I would say, unless there's some horrible mistake, it looks at least as important a discovery as pulsars and gamma ray bursts and so on. And so these are the fast radio transients and all the sort of usual suspects that we wheeled out, coalescences of neutron stars, magnetar explosions, and all these sort of things that we know about, and it could be something completely different that we haven't yet experienced. So it's a very exciting thing. So let me, having gone through this rather discursive description, overview, if you like, of what we know and how we know it, let me sort of try and consolidate that and put on my more theoretical hat and try in a sort of quick, perhaps slightly facetious way, describe how, what all this information, to digest all this information and try and find some general principles there. And I personally believe that there are principles of cosmic particle acceleration. The way most astronomers function is they work on secret galaxies or flare stars or something like that, and they do their observations of this. They work sort of in the box with the observations of that particular object. And I think if one wants to understand particle acceleration, you should take all the clues from all the different objects and combine them into trying to determine the basic principles of what goes on. And we may not have all the mechanisms there, but I suspect the totality of what's been proposed is a good fraction of what we need. But we have to understand the details of how things go on, because plasma physics and all that goes along with it is a very subtle business, and it isn't just a matter of just doing deductive physics. You really do need empirical observations to help you understand. So let me just go through some of these principles and try and give you some definition. So the first thing is, and I feel this is, New York must be the place to show this slide, is that this is plutocracy gone mad. The 1% know nothing. We go to the Zevatrons, the largest energy particles. I can tell you this gentleman is, but I don't know who that one is. They have the energy of a home run at source. So it's about 160 joules or thereabout, and that source, that's a home run in a subatomic particle. Okay. All right. So and we give a large fraction of the cosmic energy to these very deserving particles, and there's not a lot of trickle down going on, but they, in any sort of, this is so atrociously non-thermal, and so this is, it's so far removed from Maxwellian distributions of principal thermodynamics. So this is something you've got to do, that you're not allowing these particles to collide or interact very much. You've got to accelerate them very fast using electromagnetic fields to enormous energies very quickly. And this is a general principle that one needs to understand particle acceleration. The way that astronomers, or astrophysicists I should say, they try and understand systems like this, like the ones I've been describing, is you follow the energy. I mean, this is something I learned, I was told, drilled into me when I was a student and so on. Just ask where the energy is going, ask for the pathway. Just like a biologist will follow a metabolic pathway, an astrophysicist should be very strongly concerned with where the energy is flowing in that particular system. And so, just to give you, some ideas of the energetics involved, the galactic cosmic rays, there's the total amount of energy cosmic rays made by the galaxy is about 10 to the 5th joules, requiring about 10 to the 7th supernovae, and so that means about one supernova in practice every 100 years or so, which is about what we see. And this is, huge amount of energy. The pulsars are about the same. The active galactic nuclei are prodigious creators of high-energy particles. Now, you see them in the optical and ultraviolet radiation, but they also produce prodigious amounts of energy in ultra-relativistic particles, about 10% or so. So they, again, it's a large part of their energy budget, producing the cosmic rays. And what this tells you, immediately, with the free energy available, which is already hard to account for what you see, it makes cosmic rays with enormously high efficiency. So you're not allowed to have a lot of thermal plasma physics going on and then have a few test particles rattle around and get to high energy. It does it with very high efficiency. This is a general principle of the particle acceleration, if you like. Okay. The next sort of thing I'm going to say is that this is a slightly more subtle electrodynamic point. The first one is that in order to accelerate a particle, this is tautological, you need an electric field. It's an electric field that changes the energy of a particle. A magnetic field may deflect it, but an electric field is what changes the energy. No matter whether it's in the LHC or in a supernova remnant, it's still an electric field. The magnetic fields in that sense are lazy, but if we think about this in the most primitive electrical way, then when we go put energy into high energy particles in an efficient way, we do this by essentially ohmic. We can regard this particle acceleration as an ohmic dissipation of a current, and the current is not carried by the lowly particles in the proletariat in the thermal plasma. It is carried by those self-same high energy particles themselves. There's no escape from this if you're going to do this with high efficiency. So if you want to accelerate the particles, the cosmic rays themselves should be involved in the sustenance of the electromagnetic field. I think there's really no escape from this if you're going to do things with high efficiency. Now, there are many ways of doing this. One way, of course, of doing this is just straight electrostatic acceleration. We see this in the aurora and so on in a very mild way. We see it in a much more dramatic way, not directly, but by inference, in pulsar magnetospheres, where, where the voltages are about a teravolt and so on. And actually, Fermi sees it going on in lightning with impressive efficiency as well. Okay, so where we go? Okay, now that sort of electrostatic acceleration is one way of doing it. It's a very simple way, but it's not the only way of making an electric field. A more common way, and we're not going to go into like enough detail, is a phenomenon that is first discovered by this gentleman, and it's unipolar induction, basically a Faraday wheel. We spin the Faraday wheel, and you've got if you have a flux phi here, threading some spinning object with an angular frequency omega, you will induce an EMF that's roughly the product of the angular frequency and the flux. I mean, that's simple. I mean, you can work it out in much more detail, of course. And that corresponds to a maximum energy that the particle can be accelerated to from this particular configuration. If you acknowledge that things are electromagnetic, so the only impedance in town is that of free space, which generally is what it works out to be, then that gives you a current. The product of the current and the voltage gives you essentially the power involved. And so that's just written here. And if we took the sun, it's not very impressive, but if you took the Crab Nebula, there's 30 petavolts by that spinning magnetized neutron star. If we took an active galactic nucleus with a black hole with magnetic field threading it, that'll be zettavolts. Just ring a bell, remember those high energy cosmic rays, that's the source of that. If we take a gamma ray burst, you can do 100 times that, yottavolt, 0.1 yottavolts or so on, with enormous powers and so on. So conversely, if you've got to explain a high energy particle like an ultra high energy cosmic ray, then we've got to go to a very luminous source. So these are sort of general principles. Let me just show you some simulations very quickly. I didn't have how much time have I got left? Probably not a lot. Sorry, 20 minutes. Okay, well, I can show a little bit of simulation. Okay, so here's one shown done by Anatolis because he's actually the better things done now, but this just makes the point. This is the pulsar magnetosphere. It sounds like a trivial electrical engineering problem. Maybe it was, but it took 30 years to solve it. And it's just a spinning bar magnet, but it's actually much more subtle than you might think. And so we have a sort of good understanding, thanks to numerical simulation, of how the electromagnetic fields behave and what that does next. And then here's some simulations that my colleague, is this going to work with that or not? Yes, it's going. Okay, this is my colleague Jonathan McKinney and Sasha even better than I. They've been doing simulations of black holes in galactic nuclei where there's magnetic fields around. And what you can see here in these simulations is a three-dimensional magnetohydrodynamics, fully relativistic, and they can go on for 100,000 turns of the black hole and so on. So these are stable codes. And what you can see are these jets, which I referred to, that are created by the black holes and galactic nuclei. And what was striking about these simulations, it's taught us an awful lot, and I should say that these types of simulations are like computational laboratories. They're more to teach you physics than to directly simulate. And so they throw up phenomena, and you stare at that and say, I never thought of that, but I should have. It was it's something that will happen. And one of these phenomena you can see here is this sort of hula hoop type motion like that. And that turns out to be an instability which makes sense after the fact. And it's something that can be sought observationally. It's a sort of characteristic oscillation of the black hole and its jet. And so the key message from this is that these, you can extract energy from the spinning black hole in the form of these jets. And the jets are remarkably robust and stable, and they punch their way out into the intergalactic medium, the gamma ray bursts. They can punch their way out through stars and so on. And in fact, in this particular simulation, you may have seen we artificially reversed the direction, the polarity of the field, and the jet just reconstituted itself very quickly.
So the simulation in terms of the jet precessing, is that consistent with some of the observations of precessing jets?
No, there's no. People have been looking for this observation. It's a very high frequency oscillation. It turns out it's sort of a quarter of the angular frequency of the hole, and that's sort of a nice thing because the hole has no marks on it, no fiducial marks on it, and so. But nonetheless, you can, from the space-time, you can identify the angular frequency of the hole essentially directly. And this is an n=1 instability with the orbiting gas. And people have been looking for this, but this will be at very high frequencies, not the sort of precessing jet type frequencies. And so they haven't found it yet, to the best of my knowledge. Okay. Okay, so let's just go on. That's enough of that. Okay, so let's go to another. I mentioned the shocks and so on. Let's just talk about how that works. And I'm just doing this in simple language. This is a much more sophisticated and therefore confusing subject, but at its simplest level, and I'll go back to test particles and so on. Basically, we can imagine a shock front like this, and for those who aren't used to thinking about shock fronts, work in the frame of the shock front, which in the case of supernova remnant is moving out in the interstellar medium. So in your frame, the gas is coming in from the left-hand side with some speed, we'll call it u, and going out the other side of the shock front with a slower speed, call it u by r, where r is the compression ratio. And so we have gas coming in at high speed, moving out at slow speed. The shock front is the discontinuity there. Everything is conserved crossing that shock front. Now let loose one test particle upstream from the shock front, going to the shock front and then coming out the other side, and allow it to scatter off magnetic inhomogeneities, which we know about, in the material ahead of the shock front and in the material behind the shock front. And it turns out, if you just consider this at the test particle level, then an individual particle is transmitted downstream with a distribution function that is a power law, and it's basically, if you like, a convolution of the incoming distribution of particles. This is a momentum space distribution function. P is the momentum. This is F is the density in phase space. And the key thing about this is that the slope of this power law is purely a function of the compression of the shock. Of rational physical shocks, the strong shocks, the compression is 4, and the slope of the transmitted distribution function is almost exactly what you infer from the observation of the galactic cosmic rays. So this is a very good theory. One should quit while one's ahead and think no more about it, but unfortunately people have been curious and have, over the last 20, 30 years, been thinking much more about this. It's a more subtle business, but we can see observationally in the interstellar and interplanetary medium that this mechanism works, although some of the sort of detailed physics of how that scattering occurs, that's the magnetic field and so on, we're still actively working on and don't yet have a full grasp of it, but the basic principles do seem to work very well. So let's move on. Okay, this sort of statistic, rather than one-off type acceleration, this sort of statistical acceleration rattling backwards and forwards across the shock front many times, gaining energy from the converging scatterers on either side, is usually associated with the name of Fermi, although what he was actually talking about was not shock fronts, but random clouds in the interstellar medium. Okay, moving on. Okay, so this is just some of the details, and it's obviously concerned a little bit with Voyager and so on. Let's just take one of these galactic supernova remnants and the shock associated with it. If you consider how the I'm going to just give you some idea of the complexity involved here. if you consider the particles that are only accelerated, most of them, to GeV energy, so they come from relatively low keV energies and they're made up to GeV energies, then they will have short mean-free paths and will be localized very close to the shock front. The particles at the TeV, that's 1,000 times the energy, will migrate more upstream, and those at the largest energy, say near about a PeV, will get even further upstream. They get so far upstream they won't be able to find their way back to the shock front and be further accelerated, and so that's when the acceleration will cease. So if you look at the distribution of particles far ahead of the shock front, you see it's inverted in momentum space or in energy space like that, and that is classically unstable, and so the conjecture is, although the details are not fully understood, that is the way that the magnetic field is amplified. Its instability is associated with the escaping cosmic rays. I call the sort of magnetic bootstrap mechanism, so the cosmic rays make their own scattering magnetic fields, magnetic field in homogeneities. But the reason why I think it's very important to think about this is that the recent observations, which Glenys Ferrara and others have been involved with, and I don't know whether Glenys is on the line or not, but so she is, hello. But the recent observations of ultra-high energy cosmic rays do look like, they're not conclusive, the composition is changing at the very highest energy to what looks like ion group elements. And if that's the case, then that brings into play an old idea that the source of these ultra-high energy cosmic rays are giant shock fronts formed by gas as it falls into giant clusters of galaxies. These enormous shock fronts, like the supernova remnants, but formed by gas falling into clusters of galaxies rather than the explosion pushing gas out. And so those giant shock fronts, this mechanism can work if those particles are iron, as it now appears to be the case. And the real new piece of observational evidence, which is in strong support of this in my opinion, is that X-ray astronomers have now been able to measure the entropy of gas far out into the far reaches of the cluster, the large radius of the cluster, and the entropy of the gas is enormous. It's enormous compared with the entropy of the intergalactic medium, the regular intergalactic medium, and this, the only way anywhere that's known to make such high entropy gas in such enormous volumes is through passing through a strong shock front. And indeed simulations suggest these shock fronts are there, and now with the measurement of the entropy means that those shock fronts, observationally those shock fronts are there, and a shock is a shock is a shock, and it should accelerate it by exactly the same principle scaled up as the interstellar shocks, and that makes the acceleration of iron to be the ultra-high energy cosmic rays at the shock front, I would say now the favoured mechanism for these ultra-high energy cosmic rays. But certainly, in fairness, others would disagree with that assessment. Okay, there's another very important principle at work here. It's not just good enough to accelerate particles to very high energy. They have to be able to escape. If you've got some nice accelerator and then you make an ultra-high energy cosmic ray in the middle of the most luminous object in the universe, otherwise known as a gamma ray burst, then it's going to have a hard time getting out of that environment without having catastrophic losses, making pions and all the rest of it. So this is terribly important. Propagation is very important. And so our observations of cosmic rays, both direct and inferential, are strongly conditioned by the paths that cosmic rays follow, or high energy particles follow, as they get from their source regions to where they're either detected directly or emit, so we can see radiation from them indirectly. And this is a common theme that follows in these many types of sources that I've talked about. Let's go on. And this is now the Crab Nebula, and I would like to say a little bit more about this because this is something I've been thinking about most recently. And here, as I mentioned, we get these at 300 MeV flares just at that particular energy, and they happen on timescales of hours in a region that's light years across. And that actually has a very neat explanation, that particular energy, which you can find in Landau literature if you look, and this is that if you accelerate a particle under electromagnetic conditions so that the rate of gain of energy is balanced by the rate of loss of energy through radiation, just radiation reaction, limited emission, then you automatically get a gamma ray of energy of about 137 mc squared, and so this is sort of a natural explanation for why this happens. There's sort of corrections to that, but that's basically the idea. So this is what, in general, what happens, but it hasn't explained how the particles are accelerated. And we've tried a lot of schemes, and like a new one, spent a couple of minutes just describing a new one. Let me just move on. Okay, here's one scheme that has been tried that I actually don't think works, and that is if you have magnetic field of opposite polarity, so you have magnetic field of opposite polarity like that, and so magnetic field in that direction, field in that direction, quite often you put the two fields together, then they were so-called, they call it reconnect. It's a very strange phrase, reconnect, because those field lines have never been introduced in the past. It's a bit like sort of recombination, reionization, reheating, which the cosmologists talk of. It's the first time it ever happened, but nonetheless, it happens. And so connection maybe, but anyway, they exchange partners, and associated with that is a little bit of electric field and a little bit of particle acceleration, and that is thought to be, by some, to be the explanation of what's going on. I'm a bit skeptical of this for a variety of reasons we'll look at that afterwards, but it's certainly a possibility. Another possibility that sort of works a little bit better is if you imagine a pinch, this is a sort of classic electromagnetic configuration where you just have a single current along in one direction like that, it will be encircled by a magnetic field that will squeeze in with a J cross B force, will squeeze it inwards. And that in principle can make high pressure regions that are very small in the middle like that, and we thought about that one quite a bit. And the trouble with this is basically these are horribly unstable, and they have ends, and so particles leak out the ends and so on. But in principle, it's possible. And then I would say that, yeah. Let me just go back, that one, yeah. I will make one point here, is one thing we've learned about pinches when they're in dynamics. So we do have some experimental information on these pinches. But let me just go on and say what I'm now very confused about. This is based on, and again, another laboratory plasma configuration called a spheromac, and it's very, very simple mathematically. It's just think about it as pure magnetic field that has no pressure or gravity associated with it is in that limit, and so that means the current must be parallel to the magnetic field, because J cross B will then vanish. So the current is along the magnetic field, so it's a curl B equals B. So Maxwell equation, basically. Just simple like that. There's a very simple Fermi field in fluid mechanics and so on, and so applying that things to know about these sort of things, and you can make the most simplest case. This people make these in the laboratory is what's called a spheromac, and this is one where you have magnetic field lines that go around in this sort of toroidal configuration. They also go around the torus, like there's a donut where the magnetic fields go both ways around the donut together and make this sort of spiraling pattern around. And the J is parallel to B, and the vector potential for that matter. And these are what is known as having helicity. There's an electromagnetic quantity called helicity, which is associated with this, or chirality if you want, for a physicist. And of course, it's the simplest case, but you make more complicated cases like this, where you can imagine a sort of whole range of these sort of magnetic bubbles, if you like, or magnetoids or whatever, and they're all sort of stuck together, and they've got to be confined by something on the outside, but in the middle of them they can have much, much higher pressure and have much smaller scales. And that should sound familiar from the Crown Nebula, and somewhere I think here I have a demonstration. Yeah, so here we are. I was able to solve this problem in Cartesian geometry, which is like that, and then to solve it in spherical geometry, or quasi-spherical geometry, you do it like that. These sort of structures are quite generic, and then you imagine sort of changing the boundary conditions a little bit, and these things are all better stable. That's sort of what will happen. What will happen is these individual bubbles are essentially very precarious. They are magnetic. They are magnetically sort of almost metastable, so you move them around a little bit, and the magnetic configurations are very prone to buckling. So it's a bit like squeezing a playing card or putting something on too much weight on a stroke, or something like that. They'll go so far, then they'll buckle and transition dynamically, essentially at the speed of light under these circumstances, to a completely new configuration of lower energy, releasing all that magnetic energy through a huge inductive electric field comparable in strength to the magnetic field, accelerating the particles and releasing all of that energy in a sudden burst. And that is something that I think could be responsible for what we've observed in the kind of nebula, and in fact the gamma ray bursts and jets and all the rest of it under these circumstances.
You mentioned length scales of the one light field. What is so special about that kind of length scale for this kind of bubbles?
Well, I don't know what would define. I don't know what would work in the Crab Nebula, but this is a scale that might be, say, 1% of the outer scale. And it basically has to be, basically what limits this is the Larmor radius of the energetic particles. And so the size of the smallest bubble is the Larmor radius of the most energetic particles. That really is the sort of natural limit. Okay, so let's just move on quickly. So let me say a little bit about the future, and where I think this is a very active, a lot of possibilities here. I'll just try a couple of them that I think are very exciting. There's lots of observations. This is a field full of discovery. That's, we have a lot of physics students spend 15 years measuring what we expect to measure. This is one that continually confounds us and surprises us. There are new facilities coming online which ought to do the same. There's a big X-ray telescope coming. There's a major facility to do TV astronomy. There's a hope, I don't know whether this is actually going to happen, an orbiting observatory to do the highest energy cosmic rays, and perhaps the square kilometre array, which will also be estimated. We've lots of ways of looking at the transient sky. Here are just some of them. And then VLBI, I'll say a little bit more about that in a moment. On the theoretical front, the field is being transformed. I'm just trying to give you a little bit of a flavour of this by numerical simulations. Numerical simulations are not necessarily directly fiducial to the circumstance at hand, or completely fiducial, but are experiments that you can perform that teach one an awful lot. And then finally, a thing that I'd be getting more involved in again, which I think is now entering a new phase, as I said a little bit about Sandia and so on, but there's lots of high energy density experiments that are now properly diagnosed, so you can really see plasmas radiant tooth and claw and see what they actually do, rather than what some applied mathematician claims they might do in the highly specialized high symmetry configuration. So the combination of numerical simulations and high energy physics should move this sort of plasma physics along quite a long way. Just to bring out a couple of highlights. One is that I mentioned ALMA, the radio telescope. There's a plan to actually do long baseline interferometry at sub-millimeter wavelengths using ALMA as the core. And if this works, and it's a tremendously challenging experiment, you could be almost imaging the central black hole in our galaxy and in the nearby galaxy in the Virgo cluster. And that would be a very exciting prospect to actually almost image that. At the moment, the state of the art is to see interferometric fringes on the scale of 10 times the black hole. So that's very exciting. And then, and that, of course, that's a simulation, so it's exactly what will be mapped by the radio telescope, you can bet. And let's move on. Okay, I thought I had one more. Okay, anyway, so let me just conclude with these sort of general thoughts that I really think it is an exciting time in high energy astrophysics, and we still have new frontiers and telescopes to explore them with, and generally speaking, it's still in the stage of unscripted discovery. And so things are being discovered relatively fast. I do believe that this is, for the fundamentalists, this does bring up issues of basic physics. It may not be the same as discovering where supersymmetry is now or not, but what one's seen is, poking in areas where no one has looked before, and where you may make unscripted discovery, but also you are challenging in things like these rapid flares. One is really challenging, pushing physics that we thought we understood to the limits. And then historically, and I believe that actually in the future, the laboratory plasma physics and accelerator physics has had a sort of mutual interplay with astrophysics, sort of high energy astrophysics, and I think that actually will continue. I can document it if you want it. One of the sort of sad things is because it's very hard to get all these things to pay for all of these things. So a lot of the fields that were actually pioneered in the United States are actually going to happen, but they're going to be sort of led elsewhere. But I hope at least we'll be able to be a significant part of it. So the future is pretty good. So thank you very much for your time.
Your model of the particles being accelerated by the shocks in these large clusters, why did you say that that's supported by the change in composition from protons to ions?
Oh, the point is you've got to get a particle up to an energy of about a zeta electron volt. And if you start off, say, with iron, with a charge of 26, then you do much better.
I see.
Yeah. Okay, because it's the energy that we really measure. And so it's very hard to imagine a proton being accelerated under the conditions of velocity, magnetic field, and size associated with the shock fronts. But iron is I think, viable. The same sort of thing happens in the interstellars. You go into the knee, you see the composition change. So the very highest energy particles accelerated by the galactic supernova remnants, and those turn out to be heaviest too.
You argued that these accelerators can't be anything like bombs in the sense that they very efficiently put energy into a very small number of particles and leave behind everything else at much lower energy. It's not thermal. They don't look thermal at all. But these astrophysical sources are very I don't even know what I'm asking. The astrophysical sources are these very sort of just chaotic, not designed objects. They're in some sense thermal. They aren't thermal, obviously, but they are not carefully designed. Like if we were designing a device on Earth that was going to make do the same kind of acceleration, it wouldn't look anything like a galaxy cluster.
Well, I think there's two types of it. I mean, if you're going to be inspired by particle accelerators, you're looking by trying to make large potential differences. Now, particle accelerators are a carefully engineered thing where you use particles or whatever to go from one step to the next. And each time you do, you get it in sort of phase, so it's going to go like that. That's, a sort of the supernova remnant is an implementation of that, and it's only the question of scale that prevents one from demonstrating this in the laboratory. But basically, we're getting several you get a gain in energy of order U over C every time you cross the shock front moving the speed U. And you do that C over U times, and then some statistical distribution gives you a power law. So, in some sense there's a similarity there. If you take the unipolar induction, which does seem to be a generic acceleration mechanism, there you are creating a large EMF directly. And that's like a Van de Graaff generator or something like that. It's not done by spin, but you could have created it by spin rather than the series of accuracy, basically. So I think there are analogs, if you like, of those mechanisms. Not surprisingly, in the laboratory, the beat wave of wave field accelerators and so on that people are doing experiments with at the moment, they have analogs in astrophysical systems. In fact, people thought about both of them simultaneously.
Yeah, if you had a finite sized star inside a black hole, would you expect a resonant frequency based on the transit time of light across the black hole?
A star inside the black hole?
A finite sized star.
If you have a big enough black hole and a reasonable star, it can cross the event horizon without being tidally shredded. Okay. It's a billion solar mass black hole. However, soon after it has crossed the event horizon, the tidal forces will increase inexorably and tear it apart, tear apart the molecules, the atoms, the nuclei, and the composite particles.
Well, that's based if there's just one force on gravity. But if you have a back pressure, like I'm just going to say the one.
Eventually, that will happen because this will move inexorably towards quantum gravity singularity, where as far as I'm concerned, all bets are off.
Oh, you believe in a singular? Okay.
That will happen in finite time.